Okay. What I'm doing here is I'm just going to be playing with different perspectives about space drives, and the intent. I don't have a theory. I don't have a real suggestions. This is just how my mind has toyed with it over the years. In case anything that I share might help trigger other thoughts or what have you. And I hope some of you find this entertaining or it triggers other ideas. That's all there is to it. And I thought I would start with a refresher. I know that I have seen all these movies, some of them several times. I don't know how many of these are familiar to all the other people, if they recognize all of them or not. And each of them have their own special meaning. The 1953 War of the Worlds, on that one, you can all barely make it out, but they actually had 3 repulsor struts on which the thing was working. The Forbidden Planet mentioned about anti-gravity, but they didn't get any details. This was the Cavorite, the material that could shield gravity. And there's Star Trek in both forms and Star Wars. And Luke's Landspeeder, that comes in handy for playing with things. Hitchhiker's Guide to the Galaxy, which of all of these ideas here, many of them used the same things from back in the 30s, but the Hitchhiker's was the first one to actually introduce a new concept, the infinite improbability drive, for which I like. And then Buckaroo Banzai, well, I just have to mention that because I'm a fan. And if you've not seen The Explorers, it's not a great movie, but it's kind of cute how some teenage boys were able to build their own spaceship. And then the thing I liked about, I can't remember the name of this one, is the shape-changing spaceship. So anyway, all these sort of ideas, triggering thoughts and playful things. But when it comes down to it, it's like the stuff that we like there is that I want some means to move around space where I don't need to be carrying around all that propellant, and I don't want to have to rely on energy beamed to me. So have some magical way that the spacecraft will interact with the surroundings, but somehow it has to satisfy conservation, momentum, and energy in the process. And also, when contemplating these things, that the spacecraft actually has to interact with something external. There's so many ideas I've seen, especially electromagnetic ones, where you have devices inside the vehicle or pushing on each other. And then, of course, you'd like it to be controllable and strong enough to be useful. And that kind of leads you to the question, so are there any indigenous phenomena in space that we can, push against? And, can we do net forces with that? And are those forces strong enough? So that's kind of like the general things to go tracking on. But it's fun sometimes to toy with the fiction, because even when they're got logical inconsistencies, is fun. And when I first saw this one of the first thoughts that just irritated me or kept me from watching the movie straight was, what is holding that Landspeeder laterally? Okay, now obviously there's some, beam of special effects or whatever of a structural beam holding it, but that it's hovering above the ground is one piece of that. It doesn't move sideways when you brush it, that would be something really amazing. And if you had that amazing to push sideways that way, in the case of keeping it parked, well, then why do you need those jet engines? You could use that magic to push it sideways. And then also asking the questions, well, depending upon how this works, what happens if it flies over an object like a frog or something? Would the frog get squished, or is it, using technique? So the idea is to, start playing with multiple interpretations. And then there was a scene in the 1977 movie that came out when they were parked on a cliff. And this is why I was still bothered. Well, what holds this speeder from? They're overlooking a cliff, and it's like, well, gosh, if it went over the cliff, would it crash? Or if it's using some sort of ground repulsor, would it, catch in time and not splash, but, take a while before you got close enough to the ground? Or does it use some entirely different magic to where it could just go across and that wasn't an issue, and it didn't matter if the speeder slid off? So those are some of the questions that got me pondering about things, and also to illustrate, more than one way to look at the fiction. And when toying with different ideas, is like, well, what if his light speeder somehow shielded gravity? And well, then if he parked under half of a Ferris wheel, that might cause a problem, because that half of the Ferris wheel then wouldn't weigh anything and the other half would. So the Ferris wheel just keeps spinning faster and faster. So I'm using that as an illustration of when thinking about other things. And that one immediately would get you into, well, if that Ferris wheel is spinning faster and faster, energy is going into it, which means energy must be coming out of whatever magical gravity shield you devise. So to start throwing in those other comparisons as you think about these. Now for myself, before Star Wars came along, the one that I did most of my pondering with was this craft from the Star Trek. And, you know, to a 10 to 14-year-old boy, to have something that is pretty much like a panel van that can fly anywhere and have scanners to look for other interesting life forms, that's kind of a big playful thing. And what I would do is I would imagine it hovering over my driveway, and then I would ask, well, you know, if I threw rocks at it, what would happen to the trajectory of the rocks depending upon how it was levitating? And if I poked it with a stick, what would happen? Would it be like solid, or would it move? And through that, I went through a number of different variations. The idea is trying to come up with as many possible ways of coming up with things, so that if any or most of the ideas end up being dead ends, you still have some possibilities. Okay, so this first one, if I throw the rocks and absolutely nothing happens to the rocks, that's almost as if the vehicle isn't there, as if it has no mass at all, which would be interesting. And if it has no mass, does that mean it has no inertia? So if I were to poke it with a stick, would it go zooming out the other one? Okay, let's try another one. What if somehow the vehicle could magically eliminate the gravitational forces in its vicinity? So if I throw a rock at it, when the rocks are in that vicinity, they should go in straight lines and then resume their normal trajectory once out of that. Okay, another one. What if it had an anti-gravity field where it had imposed a local opposite gravitational field? In which case the rocks and other things I would think would tend to collect in that divot above it. And then the last one of these possibilities, well, what if it was just pushing down on the surrounding matter? In which case, when the rocks became in the zone of that, they would be deflected more downward than they would otherwise. And so with that sort of pondering or whatever, started to wonder about things like, okay, if you have this thing's hovering there, there's obviously the gravitational pull from our Earth, but you have all those other masses in the universe that are tugging on it too, in all the different directions. Obviously they cancel out, but I was wondering, well, how much of a tug is that if they didn't cancel out? And so if you use, and this is really rough, if you use a hemisphere of the universe and estimates for the mass density of the universe and its radius and the center of mass of what a hemisphere would be, you get that the tug of, well, half a universe in one direction is only like 4 times 10 to the minus 10 Gs. So that was really disappointing, because imagine if it was a much stronger force and you could magically alter that, play with that ever so slightly, then you can get some reasonable acceleration. Where here, it's like, my gosh, if you eliminated the gravitational pull from half of the universe, you would only get, 10 to the minus 10th Gs, which is a little disappointing. Another one, sort of asked, well, how much energy would it take to lift something? And one analogy is the moving something to infinity, and ask how much energy that takes. And it ends up being 63 megajoules per kilogram, which is actually not that much. And just for reference, I looked up what an average car battery contains, which is a bit less than that. But we're not in outrageous numbers, and a car battery really has lousy energy density. And then from the helicopter analogy, well, how much power does it take? And if you assume a 1 square meter rotor area, it's only about 20 watts per kilogram, which is like, well, that's not that much, power. So we're not talking about the kind of power levels you'd need to do for a warp drive or whatever. And maybe I should digress into that right now. When I think of space drives, I make a mental analogy of a car whose tires are pushing against whatever stuff space-time might be, in which case that's why it doesn't take much energy. But when I think of warp drives and wormholes, instead of being a road, it's almost like you have a entire civil engineering project to make a downhill ramp from where you are to where you want to go, which is a lot more energy intensive. And also that the ground has to move too. So, you know, from those two different perspectives of how much energy it would take, it's like, well, I think maybe I'll play with these ideas of, is there any way to push against space-time rather than warp it? Okay, so another way to approach it is just say, okay, what are the equations that we have for gravitational force? Or I also frequently like to use the perspectives of scalar potentials, and then you can make diagrams where in your head you can get something like a gradient, which is easy to say, oh, at the gradient, and if you put a mass there, there's going to be a force without having to do all the rest of the math. So it's like, well, what if you took these equations and you said you could modify any one of these forms and then explore what the implications of that were? And I did this, gosh, years ago, I think 1997 it was published. And the first one is like, well, what if you could mess around with the signs of the mass, which is the same thing as negative mass propulsion, or if you could do it for charge or whatever. The next idea is, well, and maybe I should wait till I get to that chart. What if you could separate the properties of mass which create a gravitational field and those which react to a gravitational field? And then the last one, there was actually a fourth one too, but could you asymmetrically affect Newton's constant locally, and what would that do? The diametric drive, it's the same thing as the negative mass. The thing here that also found useful, and this comes up in the next one, is the idea of separating out the properties of mass that create a gravitational field, the active gravitational mass, that which reacts to a gravitational field. Bondi called that the passive gravitational mass. And then he mentioned the inertial mass, but I think to be fair, to cover the possibilities, maybe split that up. What is the inertial of the inertia of the gravitational active mass and inertia of the gravitational passive mass, and then see what happens when you plug in this. And by the way, and a lot of you already know about negative mass, so I'm not going to elaborate it. And the key thing that makes that work is the negative inertia. And if you try and do these analogies with opposite charges or whatever, it doesn't work, in large part because they have all positive mass. Okay, so here's this other one, the disjunction, or perhaps I should call it the dysfunction drive, because it does not work. And I'll show you why. And this is part of the process too. Coming with these, putting it enough in the equations where then you can see the what ifs. And so the idea is what if you could magically separate out, spatially separate the part of mass which creates the gravitational field, which is here creating this divot in space-time, the gravitational scalar potential, and that which reacts to it, which all of a sudden now is on a gradient of the scalar potential. What would happen? Well, if you do that carefully and keep track of what's the active mass, what's the passive mass, what's the inertia, and so on and so forth, it comes out that this idea will only work if the inertia of the passive and active masses are different, which I don't see any clue where that is likely, which means this is like very likely to be a dead end. And that's part of the process too, of going through this and see how that turns out. This other one, and I remember in Lance Williams' talk, the idea of, well, what if you could alter Newton's gravitational constant? And when I did this years ago, I realized, and these equations are for putting in an asymmetric local perturbation, kind of like a one sine wave. And I found it interesting that the one where you're affecting Newton's constant with a exponential will not let Newton's constant pass zero, or you get excuse me, I said that wrong. That would not let the gravitational scalar potential across zero, but you still get the slopes. And I thought, well, that's kind of an interesting feature if you want to avoid negative scalar potentials. But anyway. And then there was another idea as well, what if space-time was filled with some sort of isometric, the same in all directions radiation fields, kind of like the cosmic background radiation, and you would need it to be dense. And what if you came up with different ways to asymmetrically interact with that, like a radiometer vane that absorbs the radiation on one side and reflects it on the other, or one where you affect that radiation, increasing its energy density on one side and not on the other, or if you could magically have a diode where the energy will flow through one direction and not the other. In terms of the cosmic background radiation, one that's such a small density, you don't get much force. But the other thing, that radiometer vane concept, is the absorbing side eventually heats up enough to where it also radiates later. And so both sides of that sail, unless you're taking the energy out someplace, are spewing out the same amount of radiation in both directions, so it won't work. Actually, none of these will work unless you have some sort of system that is pumping energy into it to make the effects, which that's kind of nice to know that you don't get three forces. And that would be kind of like the next place if you wanted to look at this, about how much energy would go in to get something out. So then what would you do with that? Well, for any of those that survived the first cut, unlike the disjunction did, you know, expand on the equations for the resulting accelerations. What I think would really be illuminating is to put those in terms of energy and the things of flow of energy from some source into another. I think that might be more illuminating. And for those that survive that, you know, in that process, does it trigger thoughts of natural phenomena that you've heard of that might be applicable, or areas where there's still things left unlearned? And the kind of things that fall into that category are negative mass experiments, or what is the density of empty space, the vacuum energy, or other interpretations. What's the source of inertial frames, and the proverbial unfinished coupling of the fundamental forces, gravity to electromagnetism. Okay, so let's go back to pondering levitation, where I went back later and went a little bit different about it. Making analogies to known things, and then extending these analogies so that if we were playing with gravitation. So this is very similar to what I did before, you know, zero out the vehicle or zero out the local gravity, create anti-gravity, force fields on the air, or force fields onto space itself, or something that I did not have in the ones, if you could shield gravity or ground repulse. And then ask, okay, what are some of the consequences if you could do those? And like the one when I was a kid, well, if you zeroed out the gravitational mass of the vehicle, would its inertia be zero? In which case, how would you control where it goes? And with the others, well, how far of an effect do you need to extend? The debris collecting, you know, things like this. So with when you're pushing on space-time, that brings up, okay, does space-time have a reaction mass? So anyway, things like that, which take you into the next level of unknowns. And so with the idea of pushing against space, or some space, there's the analogy of the soap boat. And if you've ever done this, this is the kind of thing you can do in your kitchen. Fill up your sink with water, put anything that floats on it, and touch a little bit of detergent behind that object, and that object will go scurrying off. So soap changes surface tension of the water, and those asymmetric forces push the craft, and water is the reaction mass. The point here is the spacecraft didn't have any propulsion on it. If it had the eyedropper of detergent on it, well, okay. So can we make analogies to space-time on that? And would space-time be a reaction mass? And can you do asymmetric changes to these things? And just over the side there listed the obvious ones I mentioned before: gravitational scalar potentials, Newton's constant, stress energy, vacuum fluctuation, Planck's constant. About the only thing I know to do with Planck's constant is, what about de Broglie waves and momentum waves and could you alter those momentum so far and then get momentum transfer? I don't have anything more developed in that. And what would happen if asymmetrically affected the speed of light? Just, other places to play the analogies with. Okay, and taking a little bit cartoon of if you were pushing against surrounding matter, but then extending that to, well, what if you pushed against all the matter of the universe rather than just locally? And what unknown does that lead you into? So let's assume we can do that. And to conserve momentum, your spacecraft moves one way and your universe moves the other way, which then begs the question, what did the rest of the universe move relative to if it's the entire universe? And so the whole questions of momentum conservation and the definition of inertial frames, realizing, yep, that's kind of an area that merits some attention. Okay, now in a simple matter, if you are trying to react against something in space, in simple terms, the more of that space that you can interact with, the greater. The higher density of indigenous mass you pick, the greater change in momentum you can get. And the more delta V that you impart to that mass, the more change in momentum you'll have to yourself. And these are like really simple sort of equations to start do that. But that's the point. You can start taking these hypotheticals, and once you start to put them in the math, you can then play other games with it and see if you run into dead ends. And as far as the indigenous mass, well, all of them have pretty low mass densities. I have no idea what to do with the Higgs one, so that's a whole unexplored area. But the vacuum fluctuation energy and space-time itself and the meaning of inertial frames, maybe those might be more promising. The vacuum fluctuation energy, and if you look at that, I have 10 to the 36 plus or minus 62 orders of magnitude, which is kind of a fair way of saying we don't really know that much about it if your uncertainty is plus or minus 62 orders of magnitude. And the one part of that density is a factor of what you pick for the upper cutoff frequency for your assumed vacuum fluctuation energy. If you pick at the Planck constant, it's an enormous, or a Planck frequency, it's an enormous number. If you pick a photon frequency that can still react with matter, it's a relatively low thing, which then begs to be alert to those concepts that consider interacting with the quantum vacuum. If you're assuming that you're interacting with photons of the vacuum energy, then you have to limit that height when calculating, well, what energy density might you be pushing on? You're going to have to limit that to the highest frequency of photons that actually impart momentum to your device, because gamma rays probably just go straight through. So, what's the highest photon that will actually interact with the device and impart momentum? That sets your upper frequency, and then you can calculate what your energy density is. And if you do that, you don't really get very promising numbers, but that's not to say it's a dead end, but that's a way of digging deeper into it. And when I tried to use the Riemannian geometry sort of things to estimate what might be a density of space-time, there's more than one formalism and more than one form, and I wasn't sure which is the right one to use, how I interpret it. That top one where you get a linear joules per meter, which is in newtons, that's a pretty high number. And if that is something that is homogeneous all around and you could affect it ever so slightly, you might still have something to go with, as opposed to what I did before with the how much gravitational pull is coming from the rest of the universe. Okay, now back to onto the coupling of the other fundamental forces. Ideally, we would like to have something that we're very good at controlling, electromagnetism, affect gravitational and inertial forces, but is that the way nature works? Are inertial and gravitational forces a function of charge and electromagnetic phenomenon, or is it the other way around? Are electromagnetic effects affected by mass? And the obvious one, light bending in a gravitational field, is pretty much indication that light is a function of gravitation, which is not the most convenient for propulsion, but it's at least a starting point. And so just playing a little bit more with that on gravitational forces, and we can describe those in terms of fields or Riemannian geometry. They're very long-range forces, which is convenient. There is a wave phenomenon then with them, the quadrupole, but the coupling with that and the amount of energy it takes to work with that is not very promising as a propulsion effect. It will affect electromagnetic propagation, the gravitational forces, either because, and well, maybe I'll get way to the chart where I use both the Euclidean and the Riemannian version. So then, does mass affect charge? We don't know. Electromagnetic forces, they're also long range, which is convenient. They also have a wave phenomenon, which has wonderful things. They've been conveniently linked to the nuclear sort of forces, but we don't have any evidence that they affect mass. And, well, maybe I'll go on. And just some other things that, you know, gravitation is much, much weaker. But here's the part where it really gets, where they branch out, where the differences are a big deal. Opposite charges can cancel, so you can create conditions where you don't have any charge, whereas you can't do that with mass. And apparently mass is all the same polarity. And all charges have mass, but do all masses have charges? Well, then it gets where you can have, where they might be carrying charges, but the charges cancel out. Here's a big one. Electric fields can be affected by conductors and insulators. But when it comes to gravity, it permeates everything. We don't have anything like a gravitational insulator to help guide it in certain places. And that's kind of, when thinking about cool tools you have, could you create a gravitational insulator, even if it was a directional thing or whatever? Okay, and then start thinking about the reference frames upon which all these things are, and I think I got these slightly out of order. Yeah, I might have these out of order, but I'll go on. Inertial frames. We still don't really realize what causes them to exist. And there's different interpretations. From the Riemannian geometry kind of thing, you know, it's usually assumed that they're just intrinsic, they're there and unalterable. But if you use the Mach's principle, depending upon which version you want to have, you can create situations where an inertial frame might not be homogeneous. And the other thing I want to point out there, very often when we think in terms of inertia, we think of it as just being a property of the mass, but it's more than that. It's a relationship between mass and space-time. You know, the F equals ma has all the terms there, not just kilograms. Okay, so in history, and starting from the bottom, we assume our inertial frames are just there, essentially the paper upon which we are drawing all the other theories. And then there was Newton's laws, which relies there to be an inertial frame to have things like conservation of momentum, and then also conservation of energy. And then special relativity took Newton's laws and modified them in the extreme where the velocities are approaching light speed, and introduced Lorentz invariance. And then adding the layer on that, the Riemannian geometry said, okay, now how do masses affect these things? And when I look at that, it's like, okay, way back in the inertial frames, if you had a Machian thing going on, that's where the masses are beginning to affect things. So why tack that on at the last step? Maybe we should go back and look at inertial frames as if they might be variable. So start with a non-physical absolute reference frame. And I use Euclidean because it's the easiest to start out with, but that's just a preference of mine. And that's just a fun representation of, or a basic representation against which you're going to derive some representation of inertial frames whose properties are a function of it, where you have the matter. Now, one thing I want to say here is that the usual interpretation of Mach's principle is that inertia here because of the matter out there, I want to change that a little bit. I want to change that to be inertial frame here because of the matter out there, and that the characteristics of the inertial frame affect inertia and other things in them. And then once you've created those new representations, how might that percolate up into the other formalities that we've already developed? And to make an analogy, as I said before, drawing on a piece of paper, where so far we've assumed inertial frames to be like fixed paper, but what if the paper wasn't fixed? Where if maybe if we drew more dots on the paper, more masses, the paper would distort, and how would we represent that? And then which case we would come up with those formalities, and then all the things that we write on that have to be a function of that. So it's one way to ask, well, how would you cascade these ideas through? Oh, okay, this the second bullet there is the inertial frame caused by the surrounding matter, and then the inertial frame affects a measured inertia. Now, the type of perspectives that I keep running into when playing with ideal space drives, not that this is how physics really is, but from the point of view of playing with space drives, if perhaps I was going to write a science fiction vehicle, wanting something to push against. And what's nice is that if you assume it's from the distribution matter of the universe, then you've also got, in a sense, an absolute reference frame, which makes a lot of other things easier. But if you go with an absolute reference frame and you talk about the connection with electromagnetism, it leads you to the optical mechanical analogy instead of the Riemannian geometry one. And I think my next chart is about those distinctions. Okay, yeah. And now this is where I have not thoroughly scanned the literature, and I probably never will at my age. But what I got left. But there's been claims that those are interchangeable phenomenon, and that there's transformations that you can go back and forth. But the way to look at the Riemannian geometry is that light follows a geodesic and curved space-time. And so in a simple way of describing space, distance is equal to how fast you're going and how much time. The reference constant is the speed of light, because that's the anchoring of special relativity and the consistency from one part of space-time to the other as the way you observe it. And then accordingly, when you have something that is warping things, both your space and time have to warp. The Euclidean geometry one is that you assume that your space is basically your reference constant, in which case the speed of light and your propagation of time measures. And then the optical mechanical analogy specifically treats the index of refraction of space as a variable with respect to gravitational scalar potential. And so that's where, this whole thing of, okay, which is a function of the other? And this is a case where you can say in nature that apparently gravitation is affecting electromagnetism. So if that's the case, let's start our representations there and see if that leads us to anything useful. So what if you wanted to create these inertial frame representations? So starting with no inertial frame properties, which is really hard to do in one's imagination. And now into this void, we presume to have a source, and I'm using this yellow, imagine it to be a sphere if you want. And now outside that sphere, there is no inertial frame properties at all. We're saying that that sphere is causing them. And so if you put a test block inside there, and then we're to move that sphere around, if indeed only that sphere is contributing to the definition of inertial frame, that test mass should move right along with it. You can also play games and say, well, what if the external space is contributing some? Well, let's try this. Well, what if you had two overlapping inertial frames? And if you want a mental model to play with that, what if you had two spherical mass shells and use the kind of the old ideas where the gravitational scalar potential is somehow related to a Mach-ing frame. And now you move those frames relative to each other and ask, where is the test mass? Well, if only the yellow frame existed, the test mass would still be coincident with the yellow frame. If only the blue frame existed, it would stay coincident with the blue frame. If both of them are contributing proportionally, it will be somewhere in between. So this can get you into some mathematical models of how you might describe that. Now, I've been picking the cases of inside of ideal spherical shells where the gravitational scalar potential was flat. And so, extending this, you'd have to ask what happens on the inside. But we're not done yet. We still have more things to ask. Is that, well, what if you were to rotate something? How would that show? And again, if only the yellow frame existed and you were to rotate it, the test mass inside would stay coincident with that frame. If only the blue frame rotated, it would stay with that. And both of them contribute, it would be somewhere in between. So now, let's say if you have a variable inertial frame effect, how is it going to affect things? And I'm first going to pick the light speed, making an analogy to gravitational scalar potential, playing on that, in which case, if you had a stronger inertial frame or like a higher gravitational potential, light speed would go slower. And that's, pulling from the that analogy. But what about momentum and things like that? So what if you had a test mass and each one was pursed with the same force, or if they had the same initial momentum or energy, the one in the higher frame would move slower. And so here's where you're getting into where you're going to be affecting Newton's laws by the properties of the inertial frame that it's written on. And I don't know how to do that. And one thing I wanted to throw out, the anomalous galactic rotations, is what if out here, since they're far away from the mass of the center of the galaxy, and if you take a literal interpretation, like I was just saying about the Machian thing, then would the inertia of the more distant masses be less? And in which case, they wouldn't have as much centripetal acceleration, so they'd be less likely to fly away. Now, this does imply that if you entertain that conjecture, that the inertial mass and the gravitational mass and forces are different, which gets you into a whole other line of thing. But just showing how this might compare with unsolved things. And then what about the propagation of, if you affect part of an inertial frame, how long is it going to take before something distant feels it? Again, I'm using the spherical shell analogy, the simple thing, if that's all that exists, and there is absolutely no delay, the test mass will stay coincident with absolutely no thing. But what if there is some finite delay property of space, in which case there's going to be a delay between when you move the source masses that are creating an inertial frame to a test mass. And you would have to then include retarded potential type of formalisms in there to capture that. And so that's, I haven't really taken these, and I probably won't really do anything with them, but I thought they're fun to play with. And some other things that I thought would be fun to play with is, what if you were creating a synthetic gravitational environment inside a spacecraft? And for fun, imagine you've got one of those and you have an alien that invades your spaceship, and for fun, you dial up the intensity of that field and squash them against the floor. Okay, or what if for fun, you change the direction of the field and disorient him. So once it's normal, once the ceiling is where that is, once the wall, and so you bounce them around. And then, okay, let's say that you just keep altering how that field is oriented and smack them against all the walls just for fun. And that little mental exercise, if you notice, I was talking about magnitude, direction, and time rate of change. So if I ever get to playing with, how would you represent in equations, realizing I'd have to ball those in there. And the idea of a de Broglie drive if you could play with momentum waves, but I haven't done anything with that. So those are just some of the kind of the playful ponderings that I dealt with. And I had some others that I didn't know how to articulate. But the one point I guess is really important here when dealing with these things, it's very common to try and narrow down into one approach. And if, as an individual trying to solve these problems, that makes so much sense. But as a greater community thing, we don't know if any one of our ideas are going to be work. So if you try and come up with as many different interpretations as possible, and go ahead and use those playful thought experiments as ways of getting in there, and then take them to the next level with putting them into equations and then asking secondary things, it's a way to make some progress. So I hope that has been of use. And with that, I will entertain equations and turning off my screen share. How do I do that?
Questions?
There we go.
Thanks, Mark. That was a plethora of ideas. I've got so many ideas bouncing around my head right now that I've got brain overload. So I'm going to ask somebody else to ask a question. Anybody have any questions for Mark?
Yes, Mark here from Falcon Space. Have you watched Stargate? They actually talk about anti-gravity as well.
Oh, the Stargate thing with the wormholes? Yes, I did. And one thing, okay, this segues into another thing, but to give you, like when contemplating the transporters or even a wormhole, imagine if the realm that you're transporting to has different air pressure. So does that mean when you turn on your transporters, you're either going to be suck the air from the rest of your environment or blow out? Or what if you're beaming down to a planet that has a very different gravitational field? What is that transition like as you cross it? Which will make for fun. I mean, those are things that you can actually write equations for, your two different environments and the conditions between, and then ask, well, what if suddenly they are connected? What would happen? And then kind of begs the naive thing is coming up to your transporters or your warp drive or your wormholes of sensing what the conditions on the other side before you fully open up and match them, kind of like an airlock, to make sure that your transport is as uneventful as you would like it to be.
I'm actually asking about they talk about anti-gravity once. I actually watched the entire show. And in one episode, they were flying out to capture something in the asteroid belt or something like that. And they talked about how the craft was actually an inertial mass dampener, and it needed thrusters in order to operate. Are you familiar with this?
I'm familiar. I'm not familiar with the Stargate version. I am familiar with the Star Trek version. And on the Star Trek version, and actually this was something that when I read it in their technical manuals, I was so dismayed. The Star Trek they call their impulse drives and then their warp drives. The impulse drives turn out to be a fusion rocket. They're still using a fusion rocket, but somehow the inertia of the spacecraft is extremely low, somehow created by the inertial dampeners, and that also keeps people from bouncing off the walls when they accelerate. And then the rocket that exhaust that's coming out from the fusion somehow retains its normal mass, or perhaps they increase the mass. And it's like, okay, if you had the means to synthesize synthetic gravitation on board the spacecraft, just turn that sideways and use that to propel your spacecraft, and you wouldn't need rockets. That would be the magical spacecraft kind of thing.
It's not really meant to make sense. It's just to be entertaining. One interesting thing that I always found is that they never have enough power on these craft. They're always transferring power to the shield, and they're transferring power to weapons. The shield down to 30%. That's where all the action is. Why don't they just put a bigger power supply on?
Well, okay, here's another story. When I was a kid deciding what I wanted to do, I noticed that the space program seemed to, and I won't elaborate. I was 9 years old when humans landed on the moon, and I saw that whole progression. And this was during a time where nuclear war always seemed imminent, and it was like, oh, this space thing seems to have a peace-inducing effect, even if only momentarily. And then the International Space University, and then so many people that I know that are into space thing. It doesn't matter what country you're from, space is cool and we can share that. And so, okay, doing space will be a cool thing to do for a career. It's fun topics, and it might lead to more peaceful things. And by the time I grow up, they'll have moon bases, and rockets will be old hat, and they'll be needing to start thinking about, Star Trek type of stuff. So that's what I started thinking about way back then. Of course, the moon bases and all that never happened. And but the other part of the story is that my assumption that helping humanity figure out how to travel to the stars would really help humanity, when I calculated the energy it would take to do even a simple interstellar mission with ideal, just the kinetic energy of moving an object and stopping it, and even a relatively small object, like an automobile, and no accounting for where the power came from, you get enormous energy levels, that are like nuclear bomb, multiple nuclear bomb stuff. And then I realized that, well, the real prerequisite to have a more peaceful, or to give humanity like interstellar flight and hopefully solutions to social problems, is that we first have to master being responsible for handling that much energy rather than having the technology to go places. So that kind of put a damper on my enthusiasm for solving, space drive and warp drive things, if that might actually cause more problems than solutions. Of course, I wasn't smart enough to figure them out either, which was certainly a disappointing part that we all have to deal with in our own ways.
Also, another consideration is if they're really using that much energy and they have that much power available on board, then wouldn't we see massive nuclear explosions if one of them crashed?
Well, when on the science fiction shows, when their vehicles, like they have a containment failure or whatever go off, yeah, the explosions from those should be considerably larger than they show in the shows. I mean,
I'm talking real world, like, there's been many crashes that are pretty well documented, and none of them resulted in nuclear explosions. They were just crashed. So either there's
I misinterpreted your question then. Could you re-ask it?
Basically, if a flying saucer or these craft that we're talking about actually crashed and they were using that sort of energy of several nuclear, then there would be a danger of massive explosions, and we don't have any history of anything like that happening.
Okay, well, now if we're talking that scenario, I thought you were talking how it's portrayed in science fiction. If we assume that they have mastered using that much energy, I'm assuming that they've learned how to master it safely and have ways of either transferring it or dissipating it or whatever in safe manners. So, that kind of gets into areas of speculation where I'm not quite sure how to deal with it. Oh, yeah, something I should have brought up. If you did have a craft that could magically interact with inertial frames to push it or whatever, and so now you can accelerate it down, you're going to have the same thing on the interior, that synthetic gravity, so that the people inside don't feel the acceleration. Now, the warp drive ideas, where you're modifying space-time in its entirety, okay, that's a different situation, and that problem doesn't apply. But if you're doing it through these more naive scalar potential things, then you're going to need something inside the spacecraft to cancel out what's happening outside the spacecraft, and you need both of those. And realizing that and thinking in simple terms, the hull of the vehicle is your propulsion device, and somehow it's interacting the thing, and the walls of your interior are your compensating device. And then, so how do those interact with each other, and how would you have an energy flow there and all that? I've never really gone through it that much, other than knowing that if I wanted to play with that more, I'd have to. And so, yeah, if you had some super advanced civilization that crashed or whatever, I would hope that they would also have super advanced safety measures. Whereas, you know,
or it doesn't really take that much energy to achieve this effect. You know, it could be we're not. It could be there is a cheat. You know, a way around. You know, the amount of energy that would take to create a warp drive, and they found some way to cancel inertial mass or inertial dampener or gravity shielding effect that we're just not aware of yet.
On that, I don't really have much in the way of speculations to share. Other than that, I encourage you to contemplate that stuff and ask, okay, where would you put that energy? Because I know Jeff Landis, he's a very creative person who also writes science fiction. And we had some lunch conversations that if you did have a warp drive and it was off, and if it does indeed need all that negative energy that you can turn on and turn off, what would that be? And in turning it on and off, and when it moved faster than light, where it suddenly left, there would be a sudden absence of the mass energy of the vehicle that it had there. So do you have to replace that somehow? So anyway, there's, you know, this, the beginnings of thoughts that go into it is, well, where do you put that mass energy? Where do you put that energy? Can you contain it? How would you make it flow? And other than knowing that those are some of the questions one might ask, I have no idea how to potentially solve it.
Our theory actually works on dynamic nuclear orientation, where we're trying to orient all the nuclei of the craft and the occupants all in one orientation. And there are several theories about why this would work, but it can possibly create some sort of inertial dampening effect where, you know, at least along the axis and the plane of the spin, the craft will become weightless.
Okay, what's really an advantage for you then, if you have a concept where it requires a lot less energy to induce these effects, if you can think of any experiment then, and it doesn't have to be for a propulsion effect, all it has to do is, if you can think of something to where your energy input in will hit,
We'll let you know tomorrow how it worked out tonight.
Okay. Yeah, well, so then you're an advantage. If indeed that you can potentially do these sort of things with far less energy, then the idea of creating experiments to explore them becomes all that much easier. And hopefully you can come up with stuff.
We're working with 20 watts right now. And so far we've seen up to 18% weight loss, but we've had problems with the laminar magnetic field, which we just fixed. So hopefully it'll jump up there in the percentages.
Okay. And I also hope that there's plenty of people that are good to talk to. One that you were introduced to earlier, George Hathaway, about the, you know, making sure that your experiments are actually measuring what you think they are. And that's something, I did experiments years ago. There was what was called the Cooper anti-gravity coils. And
that's your job.
Yep, I'm listening now.
After running the various things, you know, looking, the data was all scattered, and finally saw a correlation. And what I was doing to keep me from getting biased is I was just plotting things. I had someone else do it without labeling all the axes, so I wasn't sure. And when I saw a correlation, it's like, okay, so what's that correlation? And it was the temperature of the accelerometers. And all the rest of the stuff was random. And it's like, oh, okay. Oh, yeah, that's one thing that is extremely difficult in these experiments, is obtaining or maintaining your objectivity so that you're as equally open to disproving it as proving it, and trying to isolate and make it clear what is it exactly you're measuring. And that's really hard to do.
That's why I'm here to basically take a look over the setup that that Marc's been working on here, and with the 8.5 years of calibration experience, try to find all the possible places of error. And I'll be the first to tell you that there are still errors in the system that we're working through, and there's still noise. It's not so much errors, it's more a matter of noise floor right now.
Yeah.
there's quite a bit of an issue because we are using some magnetic materials in our sample, and we're also placing those magnetic materials in the laminar magnetic field. So naturally you have torsions that are exerted on them, and you have to try to keep the sample centered between that flux point. Otherwise, if it turns, it'll affect the laminarity, and it can also exert forces and give you erroneous measurements. So we are working through that stuff still. And if it actually gets to the point where we get results where I would consider them consistent, get that reviewed otherwise by an external third party, then we can go ahead and draw it up, explain exactly what we did. And if we get something tomorrow, it'll be interesting to present it anyways. I guess we'll see if there's something worthwhile. But we're going to give it a try anyways, and we're going to try to prove ourselves wrong, because that's sort of the goal here.
Oh, I totally forgot to mention something. And this goes back to the generic things when you're looking for possible clues to start. One of the ones that I was wondering about is whether or not the astronomical redshifts that lead to the Hubble expansion interpretation are indeed expansion or something else. Because if they were something else, that would mean that space-time is absorbing energy, and that means that, okay, there might be something where we could do energy exchange for repulsive forces. Well, recently there was some work that they found astronomical objects where they could do very precise parallax measurements, compared the parallax measurements over time with the Hubble expansion of these and the redshifts, and they match. So apparently the motion interpretation of the redshifts for astronomical objects appears to match their actual motion. So that possibility has gone away.
Possibly what might be causing that parallax shift as well, or was it just an observation that they made note of?
Oh, okay. What they did is they were comparing distance measurements with parallax and distance measurements with the redshift, or distance using parallax to measure the change in distance over time, and then compared that to what the redshifts implied that it was moving at, to see whether or not they matched, and they did.
Okay. So we have a verified, at least with one study, a verified correlation between those two that needs to be looked into some more. Is that what you're saying? This study basically correlates the redshift and the parallax shift. So yeah. That's nice. Yeah. We definitely want to look into that then. That'll be interesting. I've not heard of that study yet. That's new to me.
I gotta look that up. Someone asked about it, and I know I have it in my notes and emails someplace where I talked about it. I'll have to do a scan to see I can find it and then share it with the group later.
Yeah, that would be great, because I'd really like to read through that myself.
Yeah.
It might be difficult to find. Some of these things kind of get buried in the depths of the internet.
Or disappear.
Yeah, quite often. All right, Hal, how much time are we out of time?
Probably. Oh, yeah, we're out.